look at another optimization question. If you looked at the previous video, you'll recognize the stuff here, which I've left because it's the same each time. I'm going to make up a different question and then work through the same process. So the question this time is going to do with a tin of baked beans. So you want to sell 440 milliliters of baked beans. I think that's the size that's in a normal tin of baked beans. For those of us that are engineers, let's say that's 440,000 cubic millimeters. And we're going to do it in a cylindrical tin, so the question is, what size should a cylindrical tin be to minimize the amount of metal required? Okay, so when we're going to make our baked bean tins, we want to use as little metal as possible, because obviously that's an expense. We want to keep the expense down, but we do want to sell 440 mils of beans, because some sort of market research has shown that that's how many beans people want to buy, so we're stuck with that number. And we've got to figure out how big the tin should be, so how round and how deep. Okay, let's have a go. So step one, draw a diagram. We can do that. So we're going to have a diagram of a baked bean. There you go. No, maybe not. No, it's not going to help at all, is it, actually? We want a diagram of a tin. So we need a picture of the tin that we're going to use. So let's have a diagram of our baked bean can. And when we look at that can, what are the things that we can control? Well, one of them is going to be how tall it is, which I'll call H, and one of it's going to be how big the top of it's going to be. So we're really going to be interested in the radius. So I've got two variables, R and H. Okay, so I've drawn a picture, I've defined my variables. What's next? Write an expression for the thing to maximize or minimize. Okay, so what do I want to maximize or minimize? The amount of metal required. So I need to write a formula for the amount of metal required. So let's call that A for surface area. What have I got? I've got a top, which is pi r squared, because it's a circle. And I guess I got one of those at the bottom as well. And then I've got the roundy bit around the outside. And how big is that? Well, it's that long, which is 2 pi r for the circumference of a circle, times h. So basically, if you unwrapped it and make a big rectangle out of it, that would be h high, and that length there would be the circumference of the circle, which is 2 pi r. Okay, so that's good. So we've now got a formula for the thing we're trying to maximize or minimize. Done. Write an expression using the extra info. Okay, problem here, I've got two variables, r and h. Pi is not a variable, so don't worry about that one. Neither is 2, in case you're wondering. Those things are fine, so they're just numbers. We're not scared of numbers. It's just the variables, the r and the h. We've got two of them, so we need to get rid of one of those. So write an expression using the extra info. Well, the extra info is that we've got that many cubic millimeters. So that's going to be volume. So extra information is the volume, which in this case is pi r squared h, is equal to 440,000 cubic millimeters. We're going to be working in millimeters for this thing. Okay, so I've written an expression using the extra bit of information. That's pretty exciting. Eliminate one variable from the max-min equation. So either I've got to get rid of the r's or the h. And it looks to me it's going to be much, much easier to get rid of the h, because the r's got both an r and an r squared, so it's going to be messy if I try and eliminate the r. So let's just go with eliminating the h, which means I need this one to get me h equals. So it'll be 440,000 divided by pi r squared. So substituting that into there, a equals, let's just add those two together while we're at it. 2 pi r squared plus 2 pi r, and instead of h, I can now write this thing. 440,000 divided by pi r squared. Yeah, looking okay. I've got a function now for the thing I want, and it's only got one variable in it. Again, it's a kind of a messy one. I've got a dirty great product rule going on here and a bit of quotient, which would be a pain in the neck. So before I try and differentiate it, let's tidy her up a bit. So what have I got? A equals 2 pi r squared plus, well, those pi's can cancel out. That's kind of handy. 2 times that, okay, it's going to be 880,000 over 1 r. R on the top, r squared on the bottom, leaves me 1 r. Sweet. Okay, and I'm even thinking about differentiation coming up. It'd be easier if I wrote that as 880,000 r to the power of -1. Because it's going to be easier. I can just differentiate that using the x to the power of n formula. Brilliant. Okay. Maximum or minimum occur where derivative equals 0. So I definitely need the derivative for this thing. So dA by dr is, we've got 4 pi r, differentiate that, minus 880,000 r minus 2. And we need to make that equal to 0. So turning points occur where the ADR equals 0. So that implies that this sucker here equals 0. So 4 pi r, only 1 r, minus 880,000 over r squared equals 0. That's how I've gone back from the -2 to the thing on the bottom. This is a great form for differentiating, but this is a lot nicer for doing algebra with, at least in my head. So we're going to do, we're going to chuck that over to that side. Let's do it a couple of steps here to make sure we don't lose anything. Equals 880,000 r squared. Bring the r squared up on that side to give us an r cubed. Chuck the 4 pi under here. So r equals the cube root of that dirty great number. And I haven't got a clue what that is, but I have brought a calculator with me. So here we go. What are we looking for? On cube root of 880,000 divided by 4 pi equals 41.2. 41.2 millimeters. Okay, so I think the radius of this tin should be 41.2 millimeters. Good. Okay, we're getting somewhere. What's next? Verify the nature of the turning point you have found. Ooh, okay, so I want to make sure this is a minimum. I don't want to end up making a tin that costs lots of metal. I want to make sure it's a small one. So I need to check the minimum, and to do that, we need the second derivative. So the second derivative, so dA squared dr squared, where was my first derivative? Here's my first derivative. So if I differentiate that again, I get 4 pi minus 2 becomes a plus, 176 with 4 zeros cubed. And personally, I don't even bother putting the number in and working it out. That's a positive number. When I cube it, it's going to be a positive number. When I multiply it by something big, it's going to be a big positive number. When I add something positive, it's still going to be positive. So whatever's going on, that thing's bigger than 0. That's all I need to know. And if it's bigger than 0, we have a minimum. Okay? So I know I have a minimum going on here. So when r is 41.2, the area is a minimum. Step 7, answer the question. What was the question? What size should a cylindrical tin be? I think if I just told you that the cylindrical tin was 41 millimeters across, I haven't really said what size. You probably want to know the height as well. I think I've only answered half the question, so I really need to find h as well. So how am I going to find h? Well, you can basically use any formula you've used, and looking through here, I think the smart one is this one. It tells me what h equals if I know r, which I do. Okay, so h equals 440,000 divided by pi lots of r squared. Again, not something I can do in my head. So let's have a look at this. 440,000 divided by pi lots of r, which is still on my calculator, so previous answer squared. Comes out to be 82.4. So the can is 82.4 millimeters tall with a radius of 41.2 millimeters. And now I think I've answered the question. If someone came to me and said, what size is the can going to be? If I tell them that stuff, I've told them quite explicitly what size the can should be. Okay? So it's one of these things where if you follow through the steps and just do one thing at a time, you come up with an answer that makes sense. And that's actually something which is quite useful in the real world, to be able to work through these sort of problems and find out what's going on. So, optimization.